All right, so last time we introduced the idea of a density matrix, right? So, so what was the density matrix? The density matrix idea of is something like this. Suppose that we have a box, and inside a box there is somebody sitting, and that person is throwing a die, a multi-sided die, whose probability distribution is something. And depending on the result of the die, the person is throwing out a state from a collection of states, say psi 1, psi 2, psi 3, say psi n, and each with probability say p1, p2, p3 dot dot pn. And what I'm saying is that I'm claiming that this situation cannot be represented by a vector. And let me just show you why with a little example. So, for example, suppose that the particle that is, the state that is being thrown out is a qubit. Okay, so it's a qubit. Did I introduce the notion of a qubit? Probably not. It's a two-level system. So, for example, the spin of the electron can have spin up or spin down. And such a system, which has a two-dimensional Hilbert space, is known as a qubit. A qubit is short for a quantum bit. Okay, so a qubit plays an important role in quantum information processing. So, for example, this guy and this guy, we can represent them as 0 and 1. Then any state of this two-level system can be defined in this way. So, just as in classical circuit, like electronic circuit analysis, we have some circuits and the input can be 0 or 1, and output can be also 0 and 1. A qubit basically is, these are known as a computational basis, 0 and 1. But in a quantum computer, a state can be any arbitrary linear combination of 0 and 1. So anyway, this is the name, the qubit. So we saw that for Sz, if I apply it to this guy, I get this is an eigenvalue, eigenstate with h bar by 2. And if I apply Sz on the down, then it is h bar by minus h bar by 2, right? Now you might ask, is that, what is the eigenstate of Sx? So let's call it x plus. And if you work this out, you will find that this has the same eigenvalue. And then Sx also has the other eigenvector, which is minus h by 2, x minus. And then you might say, okay, so just as, this up and down, they form a basis of your Hilbert space. Can you have x plus and x minus as a basis for the same Hilbert space? And the answer is yes. It's just like if I have a two-dimensional vector space, and this is my x-axis and this is my y-axis, if I want, I can have this as my axis, as this as my axis. I can rotate this, right? So similarly, this is as good and a basis as this. Now the thing is, because they're both equivalent, they're both bases, so you can express this in terms of this, right? So, and you can work this out. You can say, okay, what is x plus? And up to some plus sign, minus sign that I'm not going to bother about, you find something like this. And normalization, there's some normalization, like 1 over square root of 2 or something, right? And there might be an I here or something. You know, the precise form you can work out. But the idea is that suppose now we have, you know, a box from which, say, you know, qubits are coming out either in the up state or in the down state. And suppose that the probability of up state is P1 or P, and the probability of down state is 1 minus P1 or P2. Okay, so now the idea is that I can show you that if you say, okay, I'm going to try to model this as, say, square root of P1, this, plus square root of P2 of this, then that doesn't work. That's what I'm gonna. So as long as you are measuring S of Z, of course you're going to get P1 fraction of the states which will have up spin up will be P1, and the fraction of the states which will have down spin will be P2, right? But now if I want to like if I want to say measure S of Z, S of X, then what I'll have to do is that I'll have to express these guys in terms of this states. And if I do that, then what do I get? I basically will get square root of P1 plus square root of P2, and then say X plus, and then plus square root of P1 minus square root of P2 X minus, right? So now suppose that P1 was 0.5 and P2 was 0.5. Then this would be 0, right? If this was 0, then, in terms of in the SX basis, this would just be X plus. So if I were to measure what's coming out in the SX basis, according to this model, I would only get spin up. I would never get spin down. Now, is that the case here? Let's see. If you look at this, we say that, okay, suppose that we have something coming out, which is a spin up. So now if I express this in terms of the X and Y basis, I get this. So if this comes out, 50% of the time I get spin up in the SX basis, and 50% of the time I get spin down in the SX basis. Similarly, if this comes out, then I get this is the state in the X basis. Again, it's the same statistics. This is 50%, this is 50%. So in total, if I measure SX in this physical situation, I still get 50% spin up, 50% spin down. Whereas if I were to try to model this situation using, this thing, state, pure state, then I would get 100% spin up. And that's not what I'm expecting I'm getting in the experiment, right? So we conclude that this is not the right way of modeling this situation. Did you follow that? Why we need a more general setup? So this is something that you will do in more detail in the tutorial. So it's fine if you didn't get every detail of that, okay?
So would you summarize this part in words
yeah, let
without
me
the
get,
mathematical side?
yeah. So the idea is that if there is a probabilistic distribution of states, psi1, psi2, dot, 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 psi n, with probability p1, p2, dot, 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 pn, this situation cannot be described in terms of a pure state. There is no wave function that is going to be able to describe this situation. Okay?
Sir, I don't think I really know what a pure state is.
A state, as we discussed it, a state in a Hilbert space, essentially a state that can be written as a linear combination. Suppose these are basis state, okay? This is the basis state. So any linear combination of that is a state, is a pure state.
That kind of makes hard to imagine an impure state like.
I haven't told you what an impure state is because I'm going to introduce it in a minute.
Uh,
Okay?
So the idea is the pure state cannot describe the uh, qubits coming out of the box, right?
Yeah. A pure state cannot describe a probabilistic mixture. Okay? So what can? So the idea is that we introduce a matrix, and the matrix is sum over I time, and inside the sum, the probability times the ket of that state, and then times the bra. So this ket times bra is a matrix. And let me just show you with the example of a qubit. So for example, if I take this thing is a 1, 0, and this thing is this, right? Because you get to this by taking the Hermitian conjugate. So if you now work out what the ket bra is, you get 1, 0 times 1, 0. This is not the usual matrix multiplication. This is an outer product. And this, the way it works is that you multiply this with every element here, 1, 0, then 0, 0. Right? So this is a 2 by 2 matrix. Similarly, if you look at this thing, you get 0, 0, 0, 1. Okay? So so this is, if your Hilbert space is n-dimensional, this is an n by n dimensional matrix. Okay? Now, we will mostly be discussing finite dimensional Hilbert space when it comes to density matrices. So this is called a density matrix. Okay? So a density matrix is the more abstract object, is the more a general object, I should say, that describes a non-pure state. A non-pure state is known as a mixed state. So a non-pure state is called a mixed state. Okay. So let's look at some examples. First, how to express a pure state as a density matrix. Well, you have the probability that the state is going to occur is 1. So a pure state is just, there is no sum. There's only one term in the density matrix, right? So, for example, this is a pure state. This is a pure state. Okay, so this is an example of a pure state. Now, one thing about pure state is that if you take the square of a pure state, so you take this guy, for example, you get 1, 0, 0, 0, 1, 0, 0, 0. This is 1, 0, 0, 0. And this is a general result. For pure states, rho square is equal to rho. Okay. Okay, now let's look at a mixed state. So say rho, suppose we have 50% chance that it'll be spin up and 50% chance it'll be spin down. Sorry, this should be up. Then the mixed state is this thing, right? Okay. Now it can be that the probability distribution is something more weird, is more complicated. Like, so it could be that, oh, this is half the chance that you're going to get spin up, and 1/4 the chance that you're going to get spin down, and then 1/4 the chance that you get x plus. Okay. Then what is the density matrix? Well, then it is half spin up plus 1/4 spin down, and then 1/4 x plus x plus. Now what you can do is that, okay, you can just say, okay, we know that x plus is, say, square root 1 over square root of half spin up plus 1 over square root of half spin down. So you can plug it in there, and then rho will become half this and then 1/4, and here you do the math. So you get one of these, you get 4 terms, right? So you get 4 terms, so you get, you get half up, and then you get half, down, down, and then you get some cross terms, which is half up, down, and then half down, up, right? So now, if you work this out, you're going to have, this is half. This is half times 1/4 is 1/8, right? So what is 1/8 plus half?
5/8.
So this is going to be 5/8 over here, right? And then down is also 1/4, and this is half times 1/4. So this will be also 5/8, right? And then you're going to have 1/4 times half is 1/8. Then you'll have 1/8 here, and then you'll have 1/8. So this is, this is our density matrix, right? So if you want the probability, then you'd have to diagonalize it, right? So you have to find the eigenvalues. So anyway, so this is basically what a density matrix is, and this example is a lot more useful than a general definition. But let me give you the general definition. So for infinite dimensional cases, so for infinite dimensional case, your density matrix is something like, how should I say? Something like here.
So is it like the new density matrix can be shuffled in many ways to express the state?
Yes. A density matrix can be expressed in many different ways. That's a very, very good point. Okay. So something like this. So we won't really be using that continuous version of it, but I just wanted to give it to you for completeness. Okay, before I move on and say some concluding, well, I actually have a few more things to say about density matrix, but hopefully you'll get more hands-on experience in the tutorial. Do you have any questions?
What's the difference between being in a superposition of states and being in a density matrix of states?
Right. So that's exactly what this example was about. This example is, in a density matrix, it's a probability mixture, whereas in a superposition, you are essentially changing the basis in which you're looking at a state on your Hilbert space. It's still a vector in there. So these guys, a density matrix is not a vector in the Hilbert space. It's a much more complicated object. Whereas a pure state is a vector in your Hilbert space, and when you're looking at a superposition, what you're saying is that I'm looking at it from a different basis.
So like, is it, since it's a vector, so even if we change the basis, we shouldn't get a changed probability for, let's say, getting spin up. Is that the case?
Yeah, I mean when you're doing a measurement, you are choosing a basis, right? So if you change that basis, of course, you're going to get a different statistics. In principle, right? I mean, I chose 50% here, and and that's why for the density matrix, we didn't get a different statistics. But remember that in this example, when we were doing the SZ measurement, we got 50% up, 50% down. But when we do the SX measurement here in this example, we would get 100% up and 0% down.
So what I was saying, like, this just doesn't make it qualify as a vector. Is that it? Like, if it was a vector, then it should give the same value.
No, I mean, this is a vector, right? This is a vector. If I'm measuring in the Z basis, then I think your statement is a little too reductive. Okay, so let me say a few more things about properties of density matrix. So, if you properly normalize your states, then the trace of a density matrix is, of course, 1. This is just a statement of probability conservation, right? Now, the state of a system, the evolution is given by the time evolution operator, right? So which is u of t naught is given by e to the power minus I h, which is the Hamiltonian, t minus t naught by h bar. So by linearity, the way that the density matrix evolves is by u t comma t naught acting on the density matrix at some past time t naught by similarity transformation, right? Because u is unitary, it's a unitary operator, so therefore the dagger is the same as inverse. It's fine if you don't understand, unitary operator and these things. We're not going to be using it in this course. But this is how a density matrix evolves in time. And very important is that its trace is 1. Okay? Now, also, if you have a pure state, then the trace of rho squared is going to be the same as the trace of rho. As we saw, for pure state, rho squared is rho. So this is going to be 1. For mixed state, trace of rho squared is less than 1. Okay? And this is a test of mixture. Because if I give you a density matrix in some random basis, it may look like it's not pure. But if you take the trace of its square and you find that it's actually 1, then you know that it's a pure state.